On December 21st, 2022, astronomers released a single photograph that demolished 13.8 billion years of cosmic theory, and what they found hiding in the image is forcing scientists to completely rewrite the story of how the universe began. This wasn't just another pretty space picture. Buried in this image were galaxies that shouldn't exist, massive, fully formed spiral galaxies appearing just 200 million years after the Big Bang. According to everything we thought we knew about physics, these galaxies should have been small, chaotic, blob-like structures. Instead, they look like mature galaxies from the modern universe. By the end of this video, you'll understand why this single image has cosmologists questioning whether the Big Bang theory itself needs a complete overhaul, and what the discovery means for everything we think we know about reality. Let me give you the context that makes this so earth-shattering. For decades, we had a clear picture of how the universe evolved. The Big Bang happened 13.8 billion years ago. The first stars formed a few hundred million years later. Then, slowly, over billions of years, those stars gathered into the first small galaxies. Those early galaxies were supposed to be messy, irregular, chaotic. Nothing like the grand spiral and elliptical galaxies we see today. Here's the thing. That entire story was based on theoretical models and mathematical predictions. We'd never actually looked back far enough in time to see those early galaxies with our own eyes. Then James Webb Space Telescope went online. Now, with its massive mirror and infrared vision, JWST can see farther back in time than any telescope in history, and what it saw has turned cosmology upside down. Here's what most people don't realize about looking at distant galaxies. When you look at something extremely far away in space, you're not just seeing something distant. You're literally looking backward in time. Light takes time to travel, so the farther away something is, the older the light is that finally reaches us. JWST was designed to look at the universe when it was less than 1 billion years old. The cosmic dawn, when the first galaxies were supposedly just beginning to form. What scientists expected to see, small, irregular blobs, proto-galaxies. The building blocks that would eventually merge over billions of years to become the majestic spiral and elliptical galaxies we see in the modern universe. What they actually saw broke the models. Get this. The very first deep field image revealed dozens of massive, structured galaxies that appear to be only 200 to 400 million years after the Big Bang. These aren't proto-galaxies. They're massive spiral structures with well-defined disks, central bulges, and even spiral arms, features that were supposed to take billions of years to develop. Think about it. If the universe is 13.8 billion years old, these galaxies were fully formed when the universe was only 1.4% to 2.9% of its current age. That's like finding a fully grown oak tree in a forest that was planted 2 weeks ago. Scientists were shocked to discover that some of these galaxies contain as much mass as the Milky Way, our own galaxy that's had 13.8 billion years to accumulate matter and grow. The truth is, the timeline we'd built for cosmic evolution doesn't have room for this. There literally hasn't been enough time for these galaxies to form according to our models. But here's where it gets crazy. It's not just that these galaxies exist too early. It's that they're too mature, too organized, too finished. When astronomers analyzed the light from these early galaxies in detail, they found something that makes the mystery even deeper. These galaxies already contain old stars. Let me explain why that's a problem. Stars have life cycles. Massive stars burn bright and die young, some in just a few million years. Smaller stars like our Sun can live for 10 billion years or more. When you analyze a galaxy's light spectrum, you can tell what kinds of stars it contains. Young galaxies should be dominated by hot, blue, massive stars, the first generation that formed from pristine hydrogen and helium. But these early JWST galaxies show signatures of older, cooler red stars, stars that have been around long enough to evolve and age. Here's the thing. For a galaxy to contain old stars just 300 million years after the Big Bang, those stars must have formed even earlier, maybe just 100 or 150 million years after the universe began. That pushes the timeline back even further into a period when the universe was supposed to be too hot, too dense, and too chaotic for stars to form at all. Get this. Some of these galaxies also show evidence of heavy elements: carbon, oxygen, iron. Those elements can only be created inside stars and scattered through space when those stars explode as supernovae. The presence of heavy elements means not only did stars form impossibly early, but entire generations of them had to live, die, and explode before these galaxies assembled. What does this mean? The universe had to have a much more accelerated early history than we ever imagined. The timeline isn't the only problem. There's also a mass problem that's even harder to explain. When cosmologists model how galaxies form, they start with dark matter. Dark matter makes up about 85% of all matter in the universe, and its gravity is what pulls regular matter together to form galaxies. Here's how it's supposed to work. Dark matter clumps together in what we call halos. Normal matter, hydrogen and helium gas, falls into those halos, gets compressed, and eventually forms stars and galaxies. This process takes time. A lot of time. According to our best simulations, it should take at least 500 million to a billion years for dark matter halos to grow large enough and pull in enough normal matter to create galaxies as massive as what JWST is seeing. But these galaxies exist when the universe was only 200 to 400 million years old. The math doesn't work. Think about it. It's like finding a skyscraper in a city that was founded last year. There simply hasn't been enough time to build it, even if you had all the materials ready. Scientists have calculated that to form these galaxies in the available time, matter would have had to collapse and condense at rates far faster than our physics predicts, maybe 10 times faster. The truth is, either our understanding of how dark matter works is fundamentally wrong, or there's some accelerating mechanism in the early universe that we've completely missed. Here's what nobody talks about. Some physicists are now proposing that dark matter might have behaved differently in the early universe. Maybe it was colder or clumped more efficiently than it does today. Others are suggesting the early universe might have had localized regions of much higher density than we thought. Cosmic seeds that could jumpstart galaxy formation. But here's the catch. Both of these ideas require rewriting fundamental aspects of cosmology, and there's no consensus on which, if either, is correct. Now, there's an even stranger possibility that some scientists are beginning to whisper about. And this is where things get really uncomfortable for physics. Most people don't realize there's a way these galaxies might not be as early as they appear. Let me explain how we measure cosmic distances and ages. When astronomers look at distant galaxies, they measure something called redshift, how much the light has been stretched by the expansion of the universe. The farther away a galaxy is, the faster it's moving away from us, and the more its light gets redshifted toward longer, redder wavelengths. By measuring this redshift, we can calculate both how far away the galaxy is and how long ago its light was emitted, essentially how far back in time we're seeing. Here's the thing. These early galaxies have extremely high redshifts, some with values of Z10 to Z16, which corresponds to light emitted just 200 to 400 million years after the Big Bang. But what if redshift isn't only caused by cosmic expansion? Get this. There's a controversial idea that's been around for decades called intrinsic redshift, or tired light. The notion that light might lose energy over vast cosmic distances through mechanisms other than expansion. Most mainstream astronomers reject this idea because it contradicts well-tested observations. But some scientists are now asking, what if there's a small intrinsic redshift component we've been missing? If even a small fraction of these galaxies' redshift comes from something other than expansion, they could be significantly closer and younger than we think. That would give them more time to form and mature, solving the timeline problem. But here's the catch. There's no compelling evidence for intrinsic redshift, and accepting it would require abandoning huge portions of modern cosmology that have worked perfectly well for decades. The truth is, most scientists think the galaxies really are as early as they appear, which means the problem is real and our theories need fixing. There's one more aspect of these early galaxies that's driving cosmologists crazy: their structure. When you zoom in on these JWST galaxies, many of them show clear spiral arms, bars across their centers, and organized disk structures. Here's why that's shocking. Spiral arms and galactic bars form through a process called dynamical evolution. Gravity pulls stars into organized patterns, but this process requires many orbital periods. Galaxies have to rotate dozens or hundreds of times for these structures to develop and stabilize. Think about it. Our Milky Way galaxy takes about 225 million years to complete one rotation. We call this a galactic year. For spiral arms to form, a galaxy needs to complete multiple rotations, at least 5 to 10 galactic years according to simulations. But these early galaxies exist when the universe was only 200 to 400 million years old. Even if they formed immediately after the Big Bang, which is impossible, they would have had time for only 1 or 2 rotations at most. Get this. Some of these early galaxies show bars, linear structures of stars cutting through their centers. In the modern universe, bars form in mature galaxies through gravitational resonances that take billions of years to develop. The Milky Way's bar, for example, is thought to have formed relatively recently, within the last few billion years. Yet JWST is showing us barred galaxies when the universe was supposedly still in its infancy. Scientists were shocked to discover this because there's simply no mechanism in our models that can produce these structures so quickly. Here's what nobody talks about. Some researchers are now proposing that galaxy dynamics worked fundamentally differently in the early universe. Maybe gravity was stronger on galactic scales, or dark matter was distributed in ways that accelerated structure formation. But these are just guesses. The truth is, we don't have a good explanation yet. But here's what they didn't tell you when they released these images. The galaxies I've shown you so far, they're not even the most extreme examples JWST has found. In the months since that first deep field, astronomers have identified galaxy candidates with redshifts up to Z.20, meaning they appear to exist just 180 million years after the Big Bang. Some of these are so bright and massive that if their distances are confirmed, they would completely shatter every model we have for early galaxy formation. Think about it. We're not talking about tweaking the models. We're talking about fundamental problems that might require rethinking the Big Bang itself. But before we get to what this might mean for the Big Bang theory, and I promise we're going there, you need to understand one more mystery these images revealed. A mystery that connects to the very fabric of space-time itself. Here's something cosmologists expected to see in the early universe that JWST images barely show at all. The Dark Ages. Let me explain what this is. Right after the Big Bang, the universe was filled with hot, glowing plasma, protons and electrons too energized to form atoms. This plasma glowed brilliantly, and that glow is what we now detect as the cosmic microwave background radiation. As the universe expanded and cooled, about 380,000 years after the Big Bang, protons and electrons combined to form neutral hydrogen atoms. The universe became transparent for the first time. But here's the thing. Neutral hydrogen absorbs visible and ultraviolet light. So once the universe became filled with neutral hydrogen, it went dark. No stars had formed yet to light it up. This period, from 380,000 years to roughly 150, 200 million years after the Big Bang, is called the Cosmic Dark Ages. It should have ended when the first stars formed and began emitting ultraviolet light intense enough to reionize the hydrogen, splitting it back into protons and electrons. This reionization process was expected to be gradual, patchy, and incomplete until at least 500 million to 1 billion years after the Big Bang. But JWST images suggest the universe was already largely reionized by 200-300 million years. Get this. The galaxies JWST sees are shining brightly in wavelengths that should have been absorbed by neutral hydrogen if the Dark Ages were still ongoing. What does this mean? Either the first stars formed much earlier than we thought, maybe 100 million years or less after the Big Bang, or they were far more numerous and energetic than our models predicted. The truth is, the dark ages might have been much shorter than we believed, or they might not have been truly dark at all. Some physicists are now speculating that the early universe might have had exotic energy sources we haven't accounted for, maybe primordial black holes or dark matter annihilation, or something even stranger, that lit up the cosmos earlier than stars alone could have. But here's the catch. Every one of these explanations requires adding new physics we've never directly detected. And that brings us to the possibility no one wants to say out loud. Now, here's the question that's keeping cosmologists awake at night. What if the Big Bang theory itself is incomplete, or worse, fundamentally wrong? Let me be clear. I'm not saying the Big Bang didn't happen. The evidence for an expanding universe is overwhelming. Redshift observations, cosmic microwave background radiation, the abundance of light elements. These things are real and well measured. But here's the thing. The Big Bang, as we understand it, might be only part of the story. Think about it. The Big Bang theory describes what happened after the universe began expanding. It doesn't actually explain what caused the expansion or what, if anything, existed before. For decades, physicists have added patches to the theory to make it work. Inflation, a period of exponential expansion in the first fraction of a second, was added in the 1980s to solve problems with uniformity and structure. Dark matter was introduced to explain galaxy rotation and cluster dynamics. Dark energy was added to explain accelerating cosmic expansion. Get this. Right now, the standard model of cosmology says the universe is made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. That means 95% of the universe is made of things we've never directly detected and don't fully understand. Scientists were shocked to discover that JWST's early galaxies might require even more modifications. Maybe dark matter that behaves differently in the early universe, or new physics governing star formation, or mechanisms we haven't even thought of yet. Here's what nobody talks about. Some physicists are starting to ask whether the problem isn't with galaxy formation, but with our fundamental assumptions about how the universe evolved. One idea gaining traction is that the universe might have gone through multiple phases of expansion and contraction, a cyclic cosmology where the Big Bang was actually a big bounce from a previous universe. In this scenario, the early universe might have inherited structure from a previous cycle, giving galaxy formation a head start. Another idea, the universe might have regions with different physical constants or expansion rates, a multiverse scenario where we happen to live in a region that evolved differently than the average. But here's the catch. These ideas are highly speculative. They solve one problem by creating 10 new ones. The truth is, we're at a crossroads. Either we find a way to modify our existing theories to accommodate these early galaxies, maybe through tweaks to dark matter physics, or new mechanisms for rapid star formation. Or we start seriously considering that the standard cosmological model needs a complete overhaul. And this is where the emotional weight hits. For a century, cosmology has been one of humanity's greatest intellectual achievements. We went from not knowing other galaxies existed to mapping the entire history of the universe, from the Big Bang to the present day. That story felt complete, elegant, satisfying. Now, a single telescope, in its first year of operation, has found cracks in that story. Not small cracks, foundational ones. And the most exciting, terrifying part? JWST is just getting started. Every few months, it releases new images, new spectra, new data that push the boundaries even further. Some of these early galaxies are so unexpected that teams of scientists are still arguing about whether they're even real or if there's some systematic error in the measurements. Get this. One team recently announced a galaxy candidate at redshifts of 16.4, just 250 million years after the Big Bang, that appears to be more massive than any galaxy in the local universe. If confirmed, it would be like finding a blue whale in a pond that formed yesterday. It shouldn't exist. It can't exist. And yet, there it is in the data. The truth is, We're living through one of those rare moments in science when everything we thought we knew is up for grabs, when textbooks will need to be rewritten, when the story of the cosmos is being revised in real time. So what does all of this mean for the future of cosmology, and for us? Here's the thing. If these early galaxies are real, and more evidence suggests they are, then we're facing three possible paths forward. Maybe our current theories are mostly right, but we've miscalculated some parameters. Perhaps star formation was more efficient in the early universe. Maybe dark matter clumped faster than we thought. Maybe there were feedback mechanisms we missed. This is the conservative approach. It preserves the Big Bang framework while adjusting the details. But here's the catch. Every modification has to match not just the JWST data, but also decades of other observations. You can't fix one problem without breaking something else. Maybe there's a fundamental piece of physics we're missing, something that operates at extreme energies or early times that we've never been able to test in labs or observe before. This could be new types of dark matter, new fundamental forces, or exotic physics from the quantum gravity regime where quantum mechanics and general relativity meet. Get this. Some theorists are proposing that primordial black holes, formed in the first seconds after the Big Bang, might have seeded galaxy formation much earlier than normal dark matter could have. Others suggest that dark matter might undergo phase transitions at early times, changing how it clumps and interacts. These ideas are exciting because they're testable. We can look for other signatures in the data that would confirm or rule them out. This is the nuclear option. Maybe the standard Big Bang cosmology is fundamentally incomplete. Think about it. What if time itself worked differently in the ultra-early universe? What if the expansion wasn't smooth and uniform but went through violent fluctuations? Some physicists are exploring ideas like conformal cyclic cosmology, where the universe goes through infinite cycles of expansion, or ekparodic models where our universe is the result of colliding higher dimensional branes. These models could potentially allow structure to form much faster, or even inherit structure from previous cosmic epochs. But here's the truth. We're a long way from knowing which path is correct. Most people don't realize that science doesn't progress in neat linear steps. It lurches forward through periods of crisis and resolution. We're in a crisis moment right now, and moments like this are when the biggest breakthroughs happen. Here's what makes this particularly exciting. JWST is still operational. It's going to keep looking deeper, finding more early galaxies, measuring their properties in more detail. Within the next few years, we'll have hundreds or thousands of these early galaxies cataloged. We'll measure their ages, masses, compositions, and structures with unprecedented precision. That data will either confirm that these galaxies are truly as impossible as they seem, forcing a major theoretical revision, or it'll reveal subtle effects we've been missing that reconcile them with our models. Either way, we'll learn something profound. But wait, there's more. JWST isn't alone. Ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope will come online in the next few years, giving us complementary views. NASA's Nancy Grace Roman Space Telescope will survey huge areas of sky, finding even more early galaxies. And future missions, like the proposed LUVOIR or HabEx concepts, could push even deeper into cosmic time. Think about it. We might be on the verge of witnessing the very first stars that ever formed, population 3 stars made of pure hydrogen and helium, massive and brilliant, that have never been directly observed. Or we might discover that the universe's first billion years were far stranger and more violent than we ever imagined. The truth is, these discoveries raise as many questions as they answer. If galaxies formed this early, what does that mean for the first black holes? For the chemical enrichment of the universe? For the possibility of early planet formation? And even early life? Get this. If massive galaxies existed just 200 million years after the Big Bang, and if some of them contained rocky planets, then the first potentially habitable worlds could have formed billions of years earlier than Earth. Life on Earth took about 4 billion years to evolve from simple cells to technological civilization. If habitable planets existed 10 billion years ago, when the universe was just 3.8 billion years old, then any civilizations that arose there would have had a 10 billion year head start on us. Think about what humanity might achieve in 10 billion more years of development. The implications are staggering, and it all started with one photograph. Right now, as you watch this video, JWST is collecting light from galaxies so distant that their light has been traveling toward us since before Earth even existed. Every exposure, every spectrum, every photon it captures is a piece of the cosmic puzzle. And we're watching the picture change in real time. 100 years ago, we didn't even know other galaxies existed. 50 years ago, we didn't know the universe was accelerating. Today, we're discovering that the early universe was far more complex, far more dynamic, and far more mysterious than we ever imagined. The story of the cosmos is being rewritten, and you're here to witness it. A single image changed everything. The question now is, what will the next one reveal?